So let's get into things. Oh, go ahead. So we're on 3.7 there is what we're starting with. And we're going to talk about something called related rates. Okay? And essentially these are just some like, it's for relating rates. Okay, we're going to be looking at taking a kind of context, a situation, so different kinds of things where it might be, I don't know, like application kind of stuff, and then taking the derivatives of those formulas to then relate rates. Normally taking the derivative with respect to time. Okay, so an important use of the chain rule is to find the rates of change of two or more related variables that are changing with respect to time. So changing with respect to time means that we're going to be taking the derivatives of these kind of situations with respect to what variable? T, because we normally use T. We normally use T, right? And so it'll be d something over dt. Okay? And so in other words here, right, if we have x's and y's showing up in our original formula where we're relating some variables, and if we want to now relate their rates, we would take the derivatives of those things. The derivative of x with respect to t would be dx dt. Okay, if we take the derivative of x, it would be dx dt. So it's kind of like an implicit, application of like the chain rule, and I'd say maybe even like implicit differentiation. Okay, because we're taking the derivative with respect to time of variables that aren't necessarily t. Okay, so things we want to be able to do here. When we approach a problem, we want to be able to kind of identify the different kind of things or variables that kind of would be changing in a problem. So, for example, when a balloon is inflated, okay, how could we maybe describe the shape of a balloon roughly? Now, obviously, it's not going to be a perfect version of this, but how would we describe the shape of a balloon maybe? Okay, a circle two-dimensionally, but of course, three-dimensionally, we would call it a what? A sphere, right? Okay, a sphere. And so we're going to refer to this thing as a sphere. So when a balloon is inflated, there are numerous characteristics or variables of the balloon that are changing as time goes on. So one thing that's going to be changing, if the balloon's being inflated, the volume will be changing. Okay? And do we remember what the volume formula is for a sphere? 4/3 pi r cubed, actually. 4 pi r squared is the surface area. But the good news is, you don't need to memorize it. You don't need to memorize it, okay? You will be given it. Okay, so 4/3 pi r cubed there. 4/3 pi r cubed. So another thing then that's changing, if the volume is changing, well, that means that the radius is also going to be changing here. Okay, that's going to be changing. Okay. Another thing that we may not think about changing here, but we're also talking about the changing of time, right? Because time is kind of elapsing here. Time is going on, so that's another thing that's changing. All right. So there's that. I'm trying to think what else. I guess we could talk about, since the radius is changing, we could also say, you could also potentially say that the diameter, so I'll say like d equal to the diameter, those things are changing. Those are very typical things we discuss, maybe or might talk about when we talk about the volume of a balloon. But of course, since the volume of the balloon balloon is being inflated, all right, we would talk about the rate of change of the volume, which of course we're talking about the derivative, right? So we could say then dv dt. Okay, the rate of change of the volume, okay, with respect to time. Given this scenario, the balloon is being inflated. Do we expect the rate of change of the volume to be positive or negative here? Positive, right? Because we're increasing the volume of the balloon there, so we expect it to be positive. Okay. So other things, right? We could talk about the rate of change of the radius, because certainly if the volume of the balloon is changing, right, the volume of the balloon is getting bigger. So we would expect then that the radius would also be changing as well, right? Because it's related directly to the volume there. And so that's, again, the rate of change of the radius. We'd expect the radius to be increasing as well. And of course, time, well, if time shows up in there, right, the derivative of time, we're going to take the derivative with respect to t, so it's going to be the normal kind of thing. And then diameter, of course, we could say, it's going to be, and this is going to be weird, I guess. Maybe I should have used a capital D there for diameter. I'll do that. Let me get a capital D and say d dt. Okay, and I just do the rate of change of the diameter. Okay, with respect to time. Okay, with respect to time. Okay. So these are all possible values, right, for this single scenario of balloons being inflated. These are all possible variables that could show up in a problem that we may need to use, right? So not only can we talk about the volume, the radius, time potentially, but really be like volume, radius, and diameter, right? We could like have all these three things show up. But then, because we're talking about the rate of change here, we're relating the rates too. We could also talk about the rate of change of the volume, the rate of change of the radius, the rate of change of the diameter, right? So, I guess 1, 2, 3, 4, 5, 6, if we leave off time there. 6 different variables there that we could be talking about in a particular problem where we're going to plug stuff in. Okay. So, just to give you an idea there about the different kind of things we could show up in one given scenario. Before we get into like a context though, like this, we're going to try it kind of on our own, kind of abstractly, all right? So in our first example, we're going to look at, it's going to say, suppose x and y are both differentiable functions of t, and x is less than or equal to 0. Okay. So basically, this is just telling us that we're able to take the derivative of x and y with respect to t. Okay. They're both functions of t, so we can take the derivative there with respect to t. Both functions are related by the equation y cubed equals 10 minus x squared y. Find dy dt when y equals 1, given that dx dt is 2 when y equals 1. Okay. So we've got some information here. Our goal is to find the value of dy dt. Okay. Given this relationship, if we want to find dy dt, what should maybe be a good first step to do with this equation? What do we do in calculus? Take the derivative. And in this case, with respect to what? Time, right? Because we want to find dy dt, the derivative of y with respect to t. So we need to take the derivative of this with respect to t. So when I take the derivative of y cubed, what is the derivative of y cubed? 3y squared, but then times the derivative of what's inside with respect to t, dy dt. Okay, right? So it's kind of like implicit differentiation. We're taking the derivative of y cubed with respect to t. So it's 3y squared times dy dt times the derivative of what's inside. Okay. What's the derivative of 10 with respect to t? 0. It's gone. So that's helpful. And then when we go to take the derivative of x squared y, what do we need to use? Product rule. Okay? So when I go to take the derivative here, to help us out, I'm going to consider it not to be minus the quantity x squared y. I'm going to consider it to be minus x squared times y like that. So I'm going to consider that minus to be with the x squared. Okay. And so then it'll be the, well, I guess I'll put a plus right here. It'll be the second y times the derivative of the first. The derivative of negative x squared is negative 2x dx dt. Again, because we're taking the derivative with respect to time, so both dy dt and dx dt are going to show up here. Okay. So second times the derivative of the first plus the first, negative x squared, times the derivative of the second. Derivative of y with respect to t, bless you, dy dt. Exactly right. Okay, so now we've gone from an equation that relates x and y to an equation that relates x and y along with rates, right? So related rates. The rates, dy dt, dx dt, okay, are all related here too, using that original equation there that was just relating the x and the y's. Right? So any questions just from that first step right there, that first step that we took? Okay, so essentially you can think of it almost like implicit differentiation, but instead of respect to x or respect to y, we're taking the derivative with respect to t. Okay, since we don't have any t's in here, we don't have any t's, taking the derivative of y cubed is 3y squared dy dt. No t's here, it's going to be a product rule, and then dx dt's and dy dt's show up in there. So far so good? All right. So at this point, if we're trying to find dy dt, and we're given some information there, what might be a good next step? Any ideas? How we should maybe proceed from here? If we're trying to solve for dy dt? Plug in the 2 for what? Dx dt, right. We're told, given that dx dt is 2, so we can use this piece of information. So anywhere I see a dx dt, aha, right here, that's a 2. What else can we plug in? 1 for y. Okay, so let's do that here. So we got 3 times 1 squared dy over dt equals 0 plus 1 times negative 2 x. So we don't have an x value, do we? No, it doesn't look like we're given x. Okay, and then dx dt, we know that's 2, so I'll plug in 2 for that. Still don't have an x value. And then dy dt. Okay. All right, so we plugged in what we were given there. Are we going to be able to solve for dy dt? Yes, but what's going to show up when we solve for dy dt? We're going to have what other variables still hanging around? X. Uh-oh. Right? What we're looking for here, and it doesn't make that explicit in the directions, but we're looking for something not in terms of x. We want to find the value for dy dt. Just like we know that dx dt is 2, we want a value, a single value for dy dt, which means we need to figure out what x is. So, bless you. So, how might we go about finding out what x is here? Yeah, Long?
We brought y into the first function.
Yes, okay, so remember that this original equation relates y's and x's. We want to find the x value when y is 1, right? Because that's when we're trying to find dy dt when y equals 1. So we can plug 1 in for the y here. So let's do that here. It's a little bit of side work. So 1 cubed equals 10 minus x squared times 1. Okay. So you got to find x. Okay. Now we solve, so we get, let's see here, 1 equals 10 minus x squared. And so we get negative 9 equals negative x squared, or in other words, x squared is 9. Square root both sides, and we get x equals plus or minus 3. Do we need to use both of these x values? How can I know which one I'm supposed to use? Right. X values must be less than or equal to 0, okay? And so while we may have just skipped over that in reading the directions, okay, don't forget, it's rare that you're given a piece of information that's not important, all right? So when you see something like this, when you're reading a calculus question, oftentimes we're tempted to just kind of skip over these things and think nothing of them, right? But this turns out to be a very important piece of information here, right? You might, in doing this problem, you might be all focused on doing this and then see this plus or minus 3 and think, okay, I've got 2 different values for x here. In fact, we only have 1 because we only want to consider x values less than or equal to 0. Okay, and so we just want negative 3 there for the x. All right, so now we can substitute that in. I'm going to simplify here some. So we have 3 dy dt equals, and then let's see here. Well, that'll be a negative 4 times x of negative 3 plus negative 3 squared dy over dt, like that. Okay, so I multiply the 2 and the negative 2x. So it'll be negative 2 or negative 4 times the negative 3 from the x there. Okay, so we'll just keep simplifying here. So let's see here. We have stuff 3 dy over dt equals 12 minus 9 dy over dt. We'll add the 9 over to combine it with the 3. So you get 12 dy dt equals 12. In other words, dy dt is 1. In this scenario, right, there's not a whole lot of context to it. It's kind of very abstract. We're just talking about x and y's. We don't really know what x and y are representing or if they represent anything. They're just variables in this case. So there's no real context or meaning here. Oftentimes, though, we will be in a context or have meaning to this. And so the final step here is to make sure that you have correct units attached to your answer. But in this case, there's no context. There's no units, so we don't need to worry about that. Okay. So questions about that process there? Question about that process? Okay, so The beautiful thing here is that we were given how those variables related. Sometimes we won't be given, well, we won't be given an equation. We'll be given a way the variables are related, but we won't always be given an equation. Okay? So now we're going to get into some more typical kind of related rate problems. Yes, you could still see problems like that, but we're going to get into actual some more typical ones now. And so we have some guidelines for you we're just going to start out with to kind of help organize your thinking, give you kind of like some steps to follow, okay? Just to, again, help with these, okay? So first thing we're going to do, and we kind of did this already, we're going to identify all the given quantities, and then also the quantities to be determined, right? It's potentially helpful to make a sketch also and label it. That can be helpful sometimes to do it too. So, you know, here we already had some given quantities, right? Y was 1, dx dt is 2, y was equal to 1, okay? We also highlighted what we were trying to find, the quantity to be determined, dy dt. Okay, so we did that. Okay, number 2, the next step then is once you've got all those quantities is to then write an equation. Usually it's geometric, so it's going to involve like area, maybe volume, okay, too, that involve the variables that are given or the ones that are or the ones to be determined. Okay, so you're going to relate the variables that you identify here in the first step in a situation or a context in number 2 using geometric kind of stuff. And again, you only are responsible for area, perimeter, okay, of shapes, volume formulas, and surface area formulas. You will be given those. Okay, so you don't need to worry about those. Okay. Once you've then set up that equation, you're going to use the chain rule and implicitly differentiate both sides of the equation with respect to time t. Okay, because all of these things will be changing with respect to time. Okay, they're going to be changing with respect to time. And then finally, after completing step 3, you will substitute into the resulting equation all known values for the variables and their rates of change. So notice in number 1, we identified given quantities, okay? And so you might be tempted, oh, if I know that, you know, x was 2, or if I know that y is 3, I'll go ahead and plug those in first, then take the derivative. No. You want to take the derivative of the original formula without anything plugged in, then start plugging in your values, okay, to relate things. And then solve, of course, for the required rate of change. All right? So let's put that into practice right here for example 2. So we've got a pebble dropped into a calm pond, causing ripples in the form of concentric circles. All right, so concentric circles are circles that all share the same center but have different radii. Okay, so something like that in the picture right there. All right, the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Okay, right? So again, the idea is you drop a pebble in a calm pond that was, you know, flat. The pebble causes ripples, right? And those rings, those circles get bigger and bigger and bigger as you know, time goes on. And so we want to find the area, at what rate is the total area A of the disturbed water changing, right? The disturbed water is like, you know, this area here where it was calm, but now it's, you know, wavy and stuff like that. Okay? So first thing we're supposed to do is identify all given quantities. So we've got some numbers here, right? Let's see. I see the radius. Radius is 4. Okay, so one of the given quantities we have is r equals 4, and I'll put that in units, 4 feet. Okay, we're told the radius is 4 feet. What is the total area? Okay. We're given another number here. We're told 1 foot per second. What's the label for that? What is it? Yeah. It's the units are in a velocity format. But in this context, it is the radius r of the outer ripple is increasing at a constant rate. This is the rate of change of the radius, 1 foot per second. So the radius of the concentric circles or whatever there are changing at a rate of 1 foot per second. So how do we write the rate of change of r? dr dt. That's right, dr dt, which is the rate of change of the radius, right? 1 foot per second. Okay? 1 foot per second. dr, change in r, feet, per time, change in time, seconds, right? Change in radius over change in time. 1 foot per second there. 4 feet is the radius then. Okay? Are there any other values, any other given quantities that we have here? What do you say? Are there any other given quantities? quantities that we know their values? It looks like not, right? It looks like we covered all of our variables here, our values, 1 and 4. There's no other numbers given. Okay? What is our quantity to be determined? The rate of change of the area, right? At what rate? So there's our key question. At what rate is the total area A of the disturbed water changing? So if we're trying to find the rate of change of the area, what is that as a variable here? dA dt. We are trying to find what is dA dt. What is dA dt? Okay, so questions on that process, just right there, how I knew anything from any of those variables there. Does anyone want me to kind of go through it again, real quick? When we re-summarize it, we're all feeling okay on that? Or we're just too embarrassed to ask a question because you think everyone else has got it, but you don't, and you don't want to be like, I don't want to be the only person asking a question. Okay, we'll keep going. So you'll maybe ask a question later. All right, so we've got our rates and our quantities to be determined. We can make a sketch and label it. I don't think that's really necessary here. All right, but number 2, okay, we want to write an equation, usually geometric, involving the variables that are given or are to be determined. So what is the equation here that we can use to relate all the given information that we've got? What's the formula we could use? Pi r squared, yeah, area formula here. We're going to relate all this stuff using the area formula. Okay? If we're talking about the rate of change of the area, in order to find the rate of change of the area, we need to start with the area formula itself, and then we'll take the derivative of it. Okay? So there's our kind of relationship. Okay? We want to find dA dt, so we need to use area first, and then we'll take the derivative of this. All right? So using the chain rule now, implicitly differentiate both sides of the equation with respect to time t. So what is the derivative of a with respect to t? 1 dA dt. Or just dA dt. All right, pi r squared. Do I need to use the product rule here? Right, no. Pi is a constant. Treat it like it's a coefficient, right? And so it's going to be the 2 from the r squared. The 2 will go out front, so it'll be 2 pi r to the 1, if you like, times dr dt, the derivative of what's inside with respect to t, so dr dt. Okay, and so now we have related rates. The r still is showing up there, that's okay, but now we have related rates. Okay, so what can go where? What can I plug in?
1 feet per second for dr dt.
1 feet per second for dr dt. And then 4 for r, because we're trying to find, if you remember, when the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So when the radius is 4 feet, at what rate is dA dt, or what rate is the area A changing? So that's dA dt. So we want to solve for dA dt. We've got all our variables or values filled in over here, so we'll just simplify it. So dA dt is 8 pi. What should our units be here? What should be squared, though? Feet squared per second. Okay? So one way you kind of figure it out here, right, is if we're talking about an area per time, right, change in area per change in time, we know that areas, right, areas are in square units. What are our units here? Well, we're talking about feet, right? Foot, feet, you can see that in the problem right there. So feet squared. And then, of course, per second because it's per time, right? Change in area per change in time. So feet squared per second. So that's one way you can do it, is just kind of like looking at the problem, seeing what units you have. However, it does kind of work out here. If you remember, like this right here, it's 2 pi. And the 2 and the pi here have no units. They're just coefficients, right? What was the units for the 4, though? Feet. Whoops. And then what were the units for the 1? 1 foot per second, like that. Okay? So, in other words, if we make this fractions over here, it's 2 pi over 1 times 4 feet over 1 times 1 foot per 1 second. right? 2 pi is just 2 pi over 1. There's no units there. 4 feet is 4 over 1 feet, right? And then 1 foot per 1 second right there. If you multiply across the top, you get 8 feet squared because it's foot times foot. And you get 1 times 1 times 1 second, so it's 1 second. So 8 pi feet squared over 1 second, or 8 pi feet squared per second. Okay? The units will help you out there too. Okay? The units will work out like that. Okay? Questions on that? That is the rate of change of the area with respect to time. When, if we suppose that the rate of change of the radius is 1 foot per second, and then at the time when the radius is 4 feet. Okay? So, questions on any of that? All right. Let's move on then. Okay. So number 3, we don't have a picture drawn, so we'll probably draw a picture for this one, okay? So air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the diameter. Find the rate of change of the diameter when the volume of the balloon is 36 pi inches cubed. Okay. So, what are the values that we're given here, right? What are the values that we're given? Volume, okay, we're given the volume at the instant when the volume is 36 pi inches cubed. So volume is going to have to be 36 pi inches cubed. Okay. So we took care of that one. All right. What's the other value we're given? Okay, so 4.5 cubic inches per minute. What is that? A rate of change of the cubic inches volume. It is volume. Yep. So it's dV dt 4.5 cubic inches. So I'm going to say inches cubed per minute. Okay. And again, so the units can kind of help guide you about what it's, what the variable would be, but also it's, in the context too here. Air is being pumped into a spherical balloon. So when you pump air in, that is changing the volume, right? You're adding volume to it by pumping in the air, right? That increases the volume of the balloon. Okay. What is the quantity to be determined? Yeah, dt, okay? So the rate of change, I'm going to use a capital D for diameter there, just to kind of differentiate it from the other lowercase d. And so that's what we're trying to find here. Okay, that's what we're trying to find. All right, so let's draw a little picture. So we'll draw a little balloon here. Okay, maybe give it like a nice little bow tie at the bottom there. Okay, so there's our little balloon. Okay. And so air goes in, and maybe this is the air hose, not the string, because otherwise, So we have air going in at a rate of dV dt there, which is 4.5. Okay, and so as a result, the balloon is expanding here, and so the diameter of the balloon, which is this distance right here, okay, we want to know at what rate is this like kind of changing. So I'm going to put like a d over dt. Okay, that's a d dt right there. So how is that changing, right? Okay. So we have a volume formula for this shape, right? We saw it earlier. We have the volume of a sphere is 4/3 pi r cubed. But what's the problem with that formula that we have? It's volume in terms of the radius. We need the volume in terms of the what? Diameter. Okay? So how can we adjust our formula here? 2 in front of the r. So how is the radius, how is the diameter related to the radius, right? So yes, 2r is equal to the diameter, but I want to rewrite this in terms of the diameter here. So what would I plug in for r? to make it in terms of d? Shelby? D over 2, right? The radius, therefore, is half the diameter. R is d over 2. So in place of the r here, we're going to have volume equals 4 over 3 times pi times d over 2 cubed. Okay, so there's our formula we're going to use to relate things. Now, let's simplify that sum because we can, right? We can simplify that sum. So it's going to be 4 over 3 times pi times d cubed over 8. And then the 4 and that 8 can simplify because it's all one big product here. So the 4 and the 8 can simplify to 1 and 2. And so we'll leave that as pi over 6. Okay, so the pi goes up in the numerator. 3 times the 2 there makes 6. Pi over 6 d cubed. Okay, it's helpful to simplify your expression sum if you can. Okay, so questions about where that came from? Okay, so now what? We've got our formula that relates things, right? We've got v equals pi over 6 times d cubed. What should we do now at this point? Remember, we're trying to find dd dt. Take the derivative with respect to time. So the derivative of v, dv dt. The derivative of pi over 6 d cubed, the 3 is going to come out front. So it'll be pi over 2 d to the second times dd dt. I'm going to use the capital D there. And now we have related rates. Rate of change of the volume equals stuff within the rate of change of the diameter there. We've taken the derivative. Now what? Plug in the numbers. Okay, so what can I plug in here? 36 pi is, sorry, plug what into the diameter? Yeah, okay, because that's the volume, right? 36 pi is the volume, not the diameter. What can we plug in, though? What number do we have here? We've got dv dt is 4.5. So you got 4.5 equals pi over 2. We don't have a diameter, and we're trying to solve for dd dt. Right, so this is what we're trying to solve for. But we have a problem here. We have another variable whose value we don't know, and we weren't given. We weren't given the value of the diameter of the balloon. But what can we do? Yes, Sean? The original equation, right? So back here we had that again, volume, and I'm going to use the simplified version here. Volume, remember, was pi over 6 d cubed. So we had this relationship between volume and diameter. We know the volume, as Bryce mentioned earlier, 36 pi. So let's plug that in for volume here. And then we'll solve for d. Okay. So while, yes, our ultimate goal is to use the related rates equation, sometimes we have to go back to the original equation, like Long did in the first problem, right? And like Sean suggested we do here. We have to go back to that first equation that we had to figure out some other missing values, right? We still need to know what the diameter is here. So let's do that. We're going to plug that 36 pi in for volume, and we'll find the diameter at that same instant when the volume is 36 pi. Okay? So we'll solve here, right? So let's multiply both sides by 6 over pi. So 36 pi times 6 over pi equals d cubed. So the pi's will cancel. And then 6 times 36 is 216. Thank you. Okay. Cube root both sides. When we cube root in equation settings, do we need to worry about plus or minus? No, right? Only for the even powered roots. For odd roots, right, if it's a cube root of a positive, your answer will be positive. If it's a cube root of a negative, your answer will be negative. So d equals 6. So you can plug the 6 in there. Okay, I'm running out of space. amount of space there. So let me just do a little bit of math here. So 6 squared is 36, right? But then times pi over 2, well, the 36 times divided by 2 is going to be 18. So this is really going to be an 18 pi. And so now I'll divide that 18 pi over here, and so we'll end up with, well, I'll go ahead and just take that next step. So 4.5 equals 18 pi dt. Okay, and then we'll divide the 18 pi over here. So you end up with 4.5 over 18 pi dt. Okay? And so there is our answer. We could put that up here if we wanted to. Okay. What would our units be here? Well, what are the diameters units? Inches. And then what are time units? Minutes, right? Minutes. So inches per minute will be what the diameters, rate of change of diameters units will be inches per minute. Okay? Questions on any of that? Yes? So yes, so we could simplify here, right? Because 4.5 and 18 do actually simplify nicely. And so yes, absolutely we can make it 1 over 4 pi inches per minute. But you can also leave it like this, because remember, right, in a free response question at least, you don't need to simplify any arithmetic if you don't want to there. So it's also fine to leave it like that, but if you want to simplify it, you can. Okay? You can simplify it. And it is good to recognize that it does simplify, because if it was multiple choice, you might need to be able to do that. Okay? Whew. How fun was that? That was pretty fun. Yeah. Questions on any of that? Okay. Everyone's completely lost? Good. All right, let's take a look at the last example. So we're only going to do this one more example here, and then we're going to call it a day from here. Okay, so just these last two, okay, A and B. All right. So example 4, the radius r of a circle is increasing at a rate of 2 centimeters per minute. At the instant the radius of the circle is 6 centimeters, find A, the rate of change of the area. Okay, so again, let's start with determining the values we know and the values we want to find, right? So, let's see, the quantity here, the first quantity, the radius of a circle is increasing at a rate of 2 centimeters per minute. That is what? dr dt. So in the first situation, right, we have dr dt is 2 centimeters per minute. Okay. What is 6? Radius. So r is 6 centimeters. Okay. We're talking about a circle, and we want to find the rate of change of the area. So that means what quantity are we trying to find? dA over dt equals what? That's our blank. So what is a formula that we can use to find the rate of change of the area of a circle? Don't take the derivative just yet, but what was the second part you were going to say, though? Area formula for a circle, which is pi r squared. This is one you will need to know, right? You need to know the area formula for a circle. Area is pi r squared. Okay? But like Sean said, right, we're going to take the derivative. So the derivative of a with respect to t, dA dt. The derivative of pi r squared, again, no product rule necessary, right? Just use the chain rule there, or I guess not the chain rule, use the power rule. So the 2 goes out front, so it'll be 2 pi, what? 2 pi r dr dt. Okay, right, plus differentiation. Okay, let's plug in what we know. dA dt equals 2 times pi times, we know r? Yes, r is 6. Do you know dr dt? Yes, it's 2. And so we get 24 pi. So dA dt is 24 pi. What would our units be there? Centimeters squared per minute. That was an easy one. Okay, all the information we needed was given to us there. Questions on that one? All right, letter B. Now we want to find the rate of change of the circumference. What is the circumference for a circle? So yeah, pi times the diameter, or 2 times pi times the radius, right? Okay, 2 times pi times the radius there. All right, you guys go ahead and go from there. Find the rate of change of the circumference. All right, so go ahead and give that one a try. Okay. Please also be sure to give me correct units. Please also give me correct units there for that one as well.
So this side too. What is the derivative of R?
Okay. Oh, it's ER over 2, right?
I'm charging my we go through the weird ones, we don't go to any longer. And usually, like, I listen to music, there's something on the way there.
Oh, yeah.
So, my battery.
Yeah.
Yep, good job. So 2 and pi are just coefficients. You just need to worry about getting rid of R and bring 2 pi Okay. There's the answer. Whoops, I meant to freeze it and it didn't freeze it. So, questions on any of that? So that's all I've got for you for today. The assignment is posted to Google Classroom, so you can go ahead and get started on that. I think there's only like 5 of them, okay? So, yep, 5 problems. Now there might be like A, B's, and C's to them, maybe, I don't know. But there's 5 numbers, okay? 5 numbers.
Could I please go to the bathroom?
Yes,
Thank you.
please.